Hello, my name is Shahriar Shahriari, and this is a lecture in a series of lectures on general topics in undergraduate mathematics. The topic of this lecture is mathematical induction. Mathematical induction is a method of proof. You use it to prove things. It's not quite the same as the inductive process in science, when you start with small things and build your knowledge up from the ground up. It's a way of proving a set of statements. We have an infinite sequence of propositions that are related in some way, mathematical statements that need proof. That's when mathematical induction comes into work. So you have P1, P2, all the way to Pn and so forth. This is an infinite sequence of related mathematical statements, and you want to prove them. Now, if you wanted to prove them one at a time, it would take forever, and we don't have forever. Therefore, we want to come up with a clever shortcut to prove all of them true without having to go through and prove P1, P2, P3, eventually P47, P1000, and so forth. Instead of that, what can you do? One method is proof by induction that sometimes works. And when it does, it's quite clever. The idea is that you don't prove each one of them. Instead, you prove that if one of them is true, then so is the next one. So if the statement P2 is true, then P3 is true. If P5 is true, P6 is true, and so forth. You don't do that one at a time for all of them. That would, again, take an infinite amount of time. But rather, once for all, you prove that if any one of them, whichever one is true, then the next one is true as well. If you can prove that if pk is true, then pk plus 1 is true, and you can do that for all k, then if you also prove P1, the first statement, a domino effect will set in. Since you have proved P1 is true, and you know that if anything is true, the next one is true. Since P1 is true, P2 must be true. If P2 is true, P3 must be true. If P3 is true, P4 must be true. If P4 is true, P5 must be true, and so on. And all the statements must be true. So that's one way of thinking of mathematical induction. There's an alternative way of thinking about it that goes as follows. We have this infinite sequence of statements that we want to prove. We prove them one by one, starting at the beginning. And this sort of has more of a feel of the inductive process in science. You start from the beginning, from P1. Presumably, these are getting more complicated mathematical statements as you go along. You start with the easiest one, P1, then you prove P2, then P3, and so forth. But if that's all you were going to do, that would amount to, again, doing an infinite number of proofs. But when you prove Pn, you remember that you've already proved P1, P2 through Pn minus 1, and therefore you can use them. You can use the fact that the smaller cases you have already proved, and you use that to prove Pn. This is another way of thinking about it. When you cast it this way, this is usually called strong induction. There will be a further video where we'll give more examples of strong induction. We will give one example in this lecture, but more to come. Now, when you do induction, you have to make sure that your statement Pn, at that nth statement, is formulated carefully. Pn, if you know that, you also know P1, P2, P3, because instead of n, you put 47, and you know what P47 is, and you have to know exactly what it means. You're going to prove this thing about if you know this statement, then you know the next one. Therefore, you have to know exactly what is it that you can use. So that you have to be very clear about what is it that you're proving using induction. What is that statement that you're proving? Now, induction just proves things for you. It doesn't help you find the answer. If you have a pattern, induction doesn't tell you, oh, because of induction, here's what the answer is. If you guess, if you conjecture what the answer is and what the pattern is, then induction can help you prove it. You can think of that as one of the shortcomings of induction. If you were just exploring things, you won't just come up and say, by induction, I know that the answer is this. By induction, you can prove that your guess was correct. We're going to start with one example of a pattern and see what I mean by having a sequence of statements that are related. Then we will state again what induction is, and then we will give 4 examples. The first one being the motivating example. The third example is from number theory. The fourth example is from graph theory. I want to add 1 plus 3 plus 5 plus 7 all the way until 1247. In other words, I want to add all the odd integers from 1 up to 1247. If I had patience, I could just sit there and add them. But that's not what I want to do. Mathematics is all about trying to find patterns and trying to be lazy. Is there a way that I could do this without adding them all? But for this particular problem, there's several ways. But I'm going to focus on one. Let's look for a pattern. Whenever you have a math problem you can't do, there's always a simpler math problem, an easier math problem that you also can't do. Do that one first. Instead of going all the way to 1247, trying to add all of those numbers up, Let's do a smaller problem. For example, what if I just add 1 and 3? I get 4. That's not hard. If I add 1, 3, and 5, what do I get? I get 9. And if I add 1, 3, 5, and 7, I get 16. At this point, do I see a pattern? And by pattern, I don't mean an exact formula, but something that strikes you as interesting. You might want to stop the video and try to come up with a pattern. If you did that, then you might notice that 4, 9, and 16 are all squares. So for example, 4 is 2 squared, 9 is 3 squared, and 16 is 4 squared. And so you might try that one more after that. So what happens if I add 9? If you add 9 to 16, you get 25. That's 5 squared. So you might convince yourself that if there's justice in the world, this adding of odd numbers always gives me a square. If that's the case, then 1 plus 3 plus 5 all the way to 1247 is going to be something squared. So again, I want to know 1 plus 3 plus 5 all the way to 1247 is what squared. Go back, look at the numbers, try to come up with a pattern. When you're done, then restart the video. If you do that, you might notice that 1 plus 3 was 4. We knew that. But 4 is 2 squared. What's that 2? One way to think about it is to say that there were 2 odd numbers, and that's why it's a 2. Or you could say that's the average of the first and the last one. 1 plus 3 divided by 2 is 2, and then square that, you get 4. Does that work? 1 plus 3 plus 5 was 3 squared. 3 is the average of 5 and 1. It's also the number of odd numbers that I'm adding. And the same with 4 squared. 4 is the average of 1 and 7. If that's true, then we might guess that 1 plus 3 plus 5 all the way till 1247 is 1 plus 1247 divided by 2. That's the average of the first and last one. And then that's squared. So that becomes 624 squared. All I have to do is multiply 624 by itself to get the answer. But do you trust me? How do we know this is true? It seemed like it's true. The pattern seems pretty compelling. We can't think of a reason why it would go wrong, but that's not a proof. A mathematical proof is not that we try different things and it seems to work. The mathematical proof has to be airtight. We have to have a very good reason for why this is true. And in fact, for this particular pattern, as I said, there are many ways of proving it. So for example, here's a proof without words. How this has anything to do with the problem that I just mentioned. There's a 1 dot here at the lower left. Then I add to it 3 dots. That's the next layer. Then I'm adding another 5 dots. 1, 2, 3, 4, 5. Then I'm adding 7. 1, 2, 3, 4, 5, 6, 7. So the total number of dots is these sums. Note that first dot, that's a square, 1 squared. When I add 3, I get another square. It's a 2 by 2 squared. And when I add another layer, then I get a 3 by 3 squared, and then a 4 by 4 square, and so forth. So this should convince you that when I'm adding all the way, I'm always going to get those squares. What I want to do is do a proof by induction. Let me now go back to what we said about induction and see what that would mean. First of all, induction was not about just one thing. I can't just prove that 1 plus 3 plus 5 plus 1247 is 624 squared. I have to generalize that. I have to have not just one statement, but a plethora of statements, a sequence of statements that I'm trying to prove. And so I have to, in some sense, make the problem harder. Instead of that one particular very specific problem about numbers, I have to bring in a variable and say, here's a set of statements that I want to prove. So Pn is going to be, instead of 1 plus 3 plus 5 all the way to 1247, I'll start with 1. I will add odd numbers, but I won't stop at 1247. I will go to an arbitrary odd number, and I'm going to write that as 2n plus 1. 2n is an even number. 2n plus 1 is always an odd number. So if n is 0, for example, this would be 1. If n is 1, this would be 3. If n is 2, this would be 5, and so forth. This is going to be the average of the first and the last one. The average of 2n plus 1 and 1 is 2n plus 2 divided by 2, and that's n plus 1. So n plus 1 is the average of the first and the second, and then squared. That's what I'm claiming. And I'm claiming this is true for n being any non-negative integer. If n is 0, then I'm just saying 1 equals 1. If n is 1, I'm saying 1 plus 3 equals 4, and so forth. Now I have a set of statements. P0 is just 1 equals 1 squared. P1 is 1 plus 3 equals 2 squared. When instead of n, you put 1, this tells you what the last term on the left is. So because you get 3, you start from 1 plus 3 and then stop. And on this side, you put n equals 1, you get 2 squared, you get 4. For P2, you get 1 plus 3 plus 5 equals 3 squared. For Pn, you get 1 plus 3 plus all the way to 2n plus 1 equals n plus 1 squared. And this continues. This Pn is not the last one. Pn is an arbitrary one. So I have this infinite sequence of propositions and I want to prove. Now, the first ones I can just check and I know they're true, but I don't know if all of them are true. What was the principle of mathematical induction? If you have an infinite sequence of propositions, to prove that all of them are true, you do two things. Prove the first one is true, we call that the base case, and then do this thing we call the inductive step, which is not to prove any of them are true, but to prove that if one of them is true, then the next one is true. If pk is true, then so is pk plus 1. And not just for a specific k, but for all positive integers. K can be 1, 2, 3, 4, 5, and so forth. Now let's do that for our various examples, starting with our original example, proving that 1 plus 3 all the way to 2n plus 1, those odd numbers added up, is n plus 1 squared. So what do I have to do? I have to do the base case, but we actually checked P0, P1, P2, P3. We checked all of those. So the beginning of the domino we know works. And then for the inductive case, we need k be an arbitrary non-negative integer. We reserve judgment on what k is. K could be 1, could be 10, could be 11. The statement pk means what? The statement when I plug in k for n, 1 plus 3 all the way till 2k plus 1 equals k plus 1 squared is true. I'm assuming that it's true. And using that, I'm going to prove that the next one, which is k plus 1, is true. Now, how do I get what that is? Instead of k, I put k plus 1, I get 2k plus 2 plus 1, which is 2k plus 3. And here I get k plus 1, which is k plus 2. So I'm assuming the first statement pk is true, and I want to prove the second statement should be true. Now, you might think we're cheating. Why do I get to assume that 1 plus 3 plus all the way 2k plus 1 equals k plus 1 squared? That's what I wanted to prove. I wanted to prove that 1 plus 3 plus 2n plus 1 equals n plus 1 squared. Now, replacing that with k, how do I get to assume that? What allows me to assume that's true? It's not that I'm assuming it's true. What I'm saying is that if it happens to be true, then the next one is true also. So there's an if then here. I'm not just saying the statement, I know it's true. If I knew that is true, then I would be done. I'm saying that if you grant me that the kth one is true, then I can convince you that the k plus first one got to be true as well. This is the power of induction, because it allows me to assume a statement that's very similar to what I want to prove. Now, how do I prove pk plus 1? I have to show you that 1 plus 3 plus all the way to 2k plus 3 equals k plus 2 squared. I can't write that equation because I don't know if it's true. You cannot start with the thing you want to prove and then manipulate both sides. You cannot do that because we don't know if that's true. And we in mathematics do not have a sequence of steps to do with statements that we don't know if they're true or not. If you knew it, that was an equality, then we can bring things to one side. We can multiply both sides by this or that. But if they're not equal, we can't do that. There are ways of getting around that if you really want to, but you can also trip yourself. And so I would suggest not doing that. So what am I going to do? I'm going to start with the left-hand side and I'm going to reserve judgment. What's that equal to? And I hope to get the right-hand side to come out. I start with the left-hand side, 1 plus 3 plus all the way till 2k plus 1 plus 2k plus 3. When we write those three dots here, that means there's everything from 3 all the way to 2k plus 3. And I wrote that the one before 2k plus 3, penultimate term, also. The last one is 2k plus 3. The one before that is 2k plus 1. Why did I write it like that? Because then I want to bracket the first group, 1 plus 3 all the way to 2k plus 1, and then plus 2k plus 3. The reason I did that is because now the stuff in the bracket is actually the left-hand side of the statement pk, and I'm assuming that pk is true. So instead of 1 plus 3 plus 2k plus 1, I can put k plus 1 squared. And so if I do that, I get k plus 1 squared plus 2k plus 3. I'm not done yet, because what I need to do is to show you that this is k plus 2 squared. So I multiply k plus 1 squared, I combine terms, and if you do that, you get that it's k plus 2 squared, and the proof is complete. Why is the proof complete? Because we proved the first statement, and we didn't prove any random arbitrary one, but we proved that if any of them is true, the next one is true. So since P0 is true, P1 must be true. If P1 is true, P2 must be true, and so on. All of them must be true. And that was our first example. Let's look at another pattern for our second example. I might ask you, what's 1 over 1 times 2? That's 1/2. Or 1 over 1 times 2 plus 1 over 2 times 3. Those dots means times. 1 times 2 down there in the denominator here, 1 times 2 and 2 times 3. These are fractions, and if you like fractions, you would like to add these. 1 over 1 times 2 is just 1/2. The second one is 1/2 plus 1/6. 1/2 is 3/6 plus 1/6 is 4/6, simplifies to 2/3. The next one is that 2/3 plus 1/12. If you do that, you get 3/4. So the question is, does this pattern continue? What is the pattern? It seems like I get 1/2, 2/3, 3/4, 4/5, and so forth. If there's justice in the world, that pattern should continue. If I can prove it, then I know that it's true. If I can't, then maybe it's not true, and maybe I should investigate further. To use induction, again, I need to write more general statement, not just any particular one, but a general one for arbitrary n, so that then I have a sequence of statements to prove by induction. 1/1 times 2 plus 1/2 times 3, all the way till 1/n times n plus 1. We're always multiplying two consecutive numbers. And it seems like what I'm getting is n/n plus 1 for n equals 1, 2, and so forth. This is what I want to prove. And I want to prove it by induction on n. That means n is the thing that we're incrementing. And we're going to look at the base case when n is 1. Actually, for n equals 1 or 2 or 3, we've already done it up here. Whenever you are doing induction on a problem that you already figured out the pattern, you most likely have done the base cases already. If not, you would have to do them separately. Now I pick an arbitrary positive integer greater or equal to 1, and I want to assume that the kth statement is true. Again, the kth statement seems like cheating because it seems very much like the thing that I want to prove, but this is the kth one, and using it, I want to prove the k plus first statement. Instead of n, I put k plus 1. And if you do that, you get the blue statement that I have at the bottom. I'm assuming that 1/1 times 2 plus 1/2 times 3, all the way till 1/k times k plus 1 is k/k plus 1. If you grant me that, then I'm going to convince you that 1/1 times 2, 1/2 times 3, all the way till 1/k plus 1, k plus 2 is k plus 1/k plus 2. And how do I do that? I start with the left-hand side of what do I want to prove, and I want to eventually get to k plus 1/k plus 2. I can't write that yet. I don't know if that's true, but I'm hoping that's true. I want to see if my wish comes true or not. Again, I noticed that the term before the last one is 1/k times k plus 1, and those terms are exactly the left-hand side of pk, so I already know the stuff in the parentheses is k/k plus 1. And I need to add that last term. It's 1/k plus 1, k plus 2. I take common denominators. The common denominator is going to be k plus 1, k plus 2. You combine them and you get k squared plus 2k plus 1. The top factors and the k plus 1 cancels. And lo and behold, we get k plus 1/k plus 2 as requested by the induction proof. And now we know that our pattern continues and the proof is complete. Third example, this is from number theory. So I might do 5 plus 2. You know what that is? It's 7. I might do 5 squared plus 2 squared. I get 29. I might do 5 cubed plus 2 cubed. I get 7 times 19. Then I might do 5 to the 4th plus 2 to the 4th. I get 641. I do 5 to the 5th plus 2 to the 5th. I get 7 times 11 times 41. I figured out what the answer is, and I factored it using prime factors. And 5 to the 6th plus 2 to the 6 is 29 times 541. So what? What pattern do I see here? There's one pattern that I see, which is that all the terms on the left have a 7 in their factor. Based on that data, I make a conjecture that if you have an odd integer, n, then 5 to the n plus 2 to the n is divisible by 7, has 7 as a factor. I look at data and I make that guess. It's just a guess. Who knows if this continues? When I raise to even powers, I get all kinds of strange numbers, and that doesn't give me confidence that there really is a pattern. And also here, I get these 7s, but I'm not getting anything else that seems to follow any pattern. So maybe that 7 is just a fluke. Maybe after a while, it'll go away. So I'm going to try to prove that by induction. And there's a little twist in the induction proof here. Base case, when n is 1, 5 plus 2 is divisible by 7. So I'm good with the first statement. Now, inductive step, I pick an arbitrary odd integer, and I assume that 5 to the k plus 2 to the k is divisible by 7. K is an odd integer. And I want to show you that the next one is also divisible by 7. But the next one is not k plus 1, but it's k plus 2, because my conjecture wasn't that it's always divisible by 7. It was that whenever n is odd. Using that, I have to show you the next statement, and the next statement comes for k plus 2. So I have to prove to you that 5 to k plus 2 to k plus 2 divisible by 7. So again, I just start with 5k plus 2k plus 2, and I have to convince you somehow that you can factor 7 from there. And just like the previous example, somehow or another, I want to get myself to a 5k plus 2k, because that's the thing I know. I know 5k plus 2k is divisible by 7. How do I know that? That's the inductive assumption. It's not that I really know that. If I can't do anything here, I can't go and say, I already knew 5k plus 2k is divisible by 7, I'm good. I'm saying if it's divisible by 7, If I can convince you that the next guy is going to be divisible by 7, then all of them will be divisible by 7. I'm going to do a little trick. I'm going to say that 5 to the k plus 2 is 5k times 5 squared, and 5 squared is 25. So it's 25 5 to the k's, and 2 to the k plus 2 is 4 times 2 to the k's. Okay, but that's not 5k plus 2k. Instead of 25 5 to the k's, I will write 21 5 to the k's plus 4 5 to the k's. If you have 25 apples, that's the same as 21 apples plus 4 apples. I did that because now I can factor a 4 from those two last ones. So I have 21 5 to the k plus 4 times 5 to the k plus 2 to the k. So what? Now I notice that 5 to the k plus 2 to the k, I know is divisible by 7. So this, whatever it is, has a factor of 7. This other term is 21 times 5 to the k, and 21 has a factor of 7. So both 21 and 5 to the k plus 2 to the k have a factor of 7, and therefore I can factor that 7 out, and therefore 5 to the k plus 2 to the k plus 2 also has a factor of 7. So this was a clever proof using induction. Our final induction example is from graph theory. I have to quickly give you some vocabulary of graphs. A simple graph is just a bunch of vertices and edges. Vertices, you can think of them as nodes, and edges are going to be pairs of vertices. In other words, edges are when you decide that two of those vertices are connected by an edge. For example, you might have your vertices are 1, 2, 3, 4, and the edges are 1, 2, 2, 3, 3, 4, and 1, 4. We don't usually write graphs like this. We usually draw them. This graph can be drawn in many different ways. Any one of these is the same graph. You have the vertices 1, 2, 3, 4. Those are the nodes. Each one of these subsets of size 2 tells you which vertices are connected by an edge, which vertices are adjacent. Because 1, 2 is an edge, we connect 1 and 2, then 2 and 3, 3 and 4, and 4 and 1. But depending on how we place them, of course, the graph will look different. This is what a graph is. So we're not having any loops or any double edges. We don't have any directions. We just have a bunch of nodes, and some of them connected to others. I want to say what a bridge is in a graph. If you have a connected graph, and a connected graph means that if you start from one vertex, you can go through edges and get to any other vertex. You don't have to have a direct edge from one vertex to another, but you should be able to get from any vertex to any other vertex. So if you have a connected graph, and if you have an edge, this edge is called the bridge. If when you remove it, then the graph becomes disconnected. Then it becomes two different parts. Let's give you an example. This is a graph. It has 6 vertices and 7 edges. Is the edge 3, 4 a bridge? What do you think? It is, because if you remove it, then the graph is disconnected. You can't go from the graph on the right to the graph on the left by walking through the edges. On the other hand, is the edge 1, 2 a bridge? It's not, because when you eliminate it, you can still get from any vertex to any other vertex. In this graph, the only bridge is the edge 3, 4. Here's another graph. This is something called a tree. In this graph, every edge is a bridge. If you take any of the edges, something is going to be left disconnected from another one. If you actually count, you will see that the number of vertices is 15 and the number of edges is 14. The number of edges is 1 less than the number of vertices. When we put absolute value of a set, we mean the size. So the number of vertices is 15, the number of edges is 14. And what I want to prove is this theorem that in a connected simple graph, if you know that every edge is a bridge, then automatically the number of edges is exactly 1 less than the number of vertices. And this is where I use strong induction, that second version of induction, where I think that, okay, I'm trying to prove this for a certain graph. Let's assume that I've already done it for smaller graphs. So again, we have a connected simple graph, and we know that every edge is a bridge. And what I want to show you is the number of edges is 1 less than the number of vertices. I'm inducting on the number of vertices of the graph. What if n equals 1? If n equals 1, then there's only one vertex. If there's only one vertex, there's no other vertices to have an edge to, so there's no edges. So every edge is a bridge. Why? Because there's no edges. So all of the edges that there are, which there aren't any of, all of them, each single one of them is a bridge. And the number of edges is 0, which is 1 less than the number of vertices, which is 1. So in that case, we're good. Every edge is a bridge, and the number of edges is 1 less than the number of vertices. Now, what about the inductive step? So now a graph G has walked through the door. It's a connected simple graph, and every edge is a bridge. I want to convince you that the number of edges is 1 less than the number of vertices, but I'm inducting on n, which means that I know that I've done the smaller cases first. I know that if I run into any connected simple graph where every edge is a bridge, but has fewer vertices, that my theorem is already true, that the number of edges of that graph is one less than the number of vertices. Let alpha be any of the edges. Pick your favorite edge and take that out. Don't take any vertices out. Let G prime be G minus alpha. So the graph you had, just take that one edge out. Now, if you take that edge out, that graph G, every edge was a bridge. So you took this guy out, you split it up. This new graph has still the same number of vertices and has one less edge, but it's split into two parts. Why? Because alpha was a bridge. And so those two parts I'm going to call G1 prime and G2 prime. Now, each of them is a connected simple graph, but I don't know how many vertices they have. This one has K of them. This one has L of them. K vertices for G1 prime and L vertices for G2 prime. And I do know that K plus L is N because N was the total number of vertices we had. And all the vertices are either in this part or in that part of the graph. And both L and K have to be less than N because none of these are empty graphs. So G1 prime and G2 prime are both connected simple graphs with fewer vertices than G, and every edge still the bridge, just like it was before. And so I can apply induction. So by induction applied to these two graphs, I know that my theorem must be true for them. So G1 prime and G2 prime must have K minus 1 and L minus 1 edges respectively. But then what can I say about the number of edges of G? The edges of G1 prime and G2 prime are edges of G. So I have at least K minus 1 plus L minus 1, but I also have that alpha that I first took out, that first edge that I took out. So this is the total number of edges of G, and there are no others. And if you add these, you get K plus L minus 1. K plus L was N, and so you get N minus 1, and the proof is complete. So you want to think about the structure of this proof a little bit. How did I do that? I said that we are trying to prove for this particular graph that the number of edges is one less than the number of vertices, but we could assume by induction that we had already proved the theorem for smaller graphs, and then we use that to prove for the original graph. Now, this is a slightly different way of using induction than those earlier examples, but it's nevertheless induction as well. And again, in a future lecture, I will give you more examples of strong induction. And if you take my course in combinatorics or my course in abstract algebra, you will see plenty of uses of this kind of strong induction in both of those courses. This is the end of this lecture, and I will see you in the next one.